So we have here an airplane flying in a horizontal circle. This would just be like an airplane taking a curve. Your given radius, your given period, and then you're asked to find speed. So we derived this formula earlier today. There isn't much else to this one. It's very basic. So 2 pi r over capital T, where T is the period. So 2. It's basically d over t, just for a circle, because 2 pi r would be the circumference. You came in late and you might have missed that. All right, so 80 looks like 81 meters per second. You guys okay with that? All right, now this is the one where you have, guys, this is where you have the option of using that new formula we derived, or you could just do it in 2 steps. Like, I'll probably just do it in 2 steps. Makes sense to me that way. So you have a period of 1 year. And of course, 1 year is going to have to be broken down into seconds. So you have 365 and a quarter days. The leap year. Every 4 years you get an extra day. So each year is 365.25 days. You guys don't know that? It's common sense. Just quickly do a Google search. What is the how long does it take for the Earth to travel around the sun? Okay, so how many excuse me, how many hours are in a day? So then the day cancels. How many seconds are in the hour? I just skipped the 60 times 60. 3,600 seconds in the hour. It's just 60 times 60. 60 minutes, 60 seconds. So we get a lot of seconds. We get 3.16 times 10 to the 1, 2, 3, 4, 5, 6, 7 seconds. Okay, so hopefully you're following along on the calculator, seeing the same numbers. That would be the period for 1 year, yeah, in seconds, because of course you have to have your standard units. And then this one here, this is not the radius of the Earth. Remember, this would be the orbital radius that you'd find on your data sheet. So it would be the radius around the sun on average, because it's not perfectly circular, but it's pretty close. You can make an approximation. So V would equal 2 pi r over t. So 2 pi multiplied by that 1.49, and then divided by that last answer. 29,666. So we got 3 significant digits. So 2.97 times 10 to the 1, 2, 3, 4 meters per second. Excuse me. Okay, so that's how quickly the Earth is hurtling around space. It's pretty fast. That's okay. We just go on our day-to-day lives, flying around space, okay. So then the acceleration, centripetal acceleration, and this is also like centripetal velocity, but it's all good. AC here, we would say v squared over r. So we don't really necessarily have to use that fancy formula. If you do it in 2 steps, that's fine as well. So take that answer and square it, and then divide it by the radius. So we get 5.9 times 10 to the minus 3 meters per second square. So the acceleration is very close to 0. Because it's got to, you think of the Earth, it's got to travel such a massive distance. Quite a long time. So like, I'm thinking to myself, if that acceleration vector wasn't that, you know, would it be quite stable living here on Earth? Yeah. Yeah? Yeah, you're probably rounding in between. You guys cool on this? Okay, the electron in a hydrogen atom moves at a speed 2.19 times 10 to the 6, very, very massive speed. And the orbital radius, 5.24 times 10 to the negative 11 meters. This is an old model of the atom from the early 1900s. It's not perfect, but it gives a sense of what's happening. Even to say that like the electron is a particle that moves like a ball around another ball, like that's even a little bit wild. It's not entirely true, but you know, this is a classical model that gives good approximation. So this is not perfect, but it gives a good idea. Okay, so V is 2 pi r over capital T, and you can see here they want us to solve for the period. Now we're into like mid-November here, and there's still some students still struggling with manipulating of equations. I just need you guys to be very aware that like if your equation has no plussing and minusing, there's no plussing and minusing anywhere in the equation, like outside these terms, it's always just strictly cross multiplication. So if you're downstairs on the right, you're upstairs on the left. These guys will switch places. 2 pi r over v. Okay, and somehow you have the speed of the electron, somehow. I'm not sure how you know that, but okay. And you have the radius of the electron as well. So you can type those in and you're good to go. So we get this ridiculous number here, 1.50 times 10 to the minus 16 seconds for 1 rotation. Now think about that. 10 to the minus 16 of a second. That is so small, it's basically 0. Like, how can you have something that small? How could you even think about that? Well, it's too hard to think about that. So what we're going to do is actually we're going to inverse it. Remember that the frequency and the period are inversely related. So on your calculator, all you have to do now, you have the button, you have the answer locally saved here. All you now have to do is hit this one here, x to the minus 1. It's underneath the math button. Just hit that. it'll say answer to the power -1, and then you get the frequency. So frequency is 1 over the period, and you get 6.65 times 10 to the 15. And the unit for frequency is hertz. So it does this many rotations or orbits or revolutions of the atom in 1 second. This button right here, x to the -1. Yeah, on the answer from the period, yeah. And later in Physics 30, you'll learn that like this, it's not like a billiard ball orbiting a planet. Like it's not like that. It's actually a wave. It's a quantum fluctuation. It's an electron field. It's just a fluctuation. It's a up and down like this, or back and forth, back and forth. It's a wave. It goes up, it goes down, it goes up, and that many times in 1 second. Yeah, that's the subatomic quantum world, and it defies logic for us. Moving on. Typical cell phone. This is very common for us. We don't even notice it. Like right now, like if you have your Bluetooth turned on right now, or your data is turned on, or your Wi-Fi is turned on, like if we were more highly developed animals, we would be able to sense the EMR in this room. Like there's actually like this electric field bouncing, electromagnetic field bouncing all over this wall, all over this room that we don't see. It's in here, but we don't see it. The stuff we do see is the white light. You can see that because your body has evolved over many years for this to happen. So like this radio signal, like you can't see radio waves, but you know they're there because you can tune a radio. So just because you can't see it doesn't mean it's not there. And it's absolutely ridiculous. Think about like if you go to the wave pool, like West Edmonton Mall or Millwoods, they have that wave pool. Or you think of the ocean, like you watch a wave, what happens to the wave? You know, it goes up, it goes down, goes up, goes down. That's a cycle. So it's like how many cycles in 1 second? Well, this one does 2 billion oscillations, 2 billion of these little back and forths, little vibrations every second. It's ridiculous. Anyways, you've probably seen gigahertz, maybe when you're looking at the specs of your phone or something like this. So frequency is 2.0 gigahertz. If you're stuck on the metric, you're not a big metric nerd like I am, you might not know what giga is, that's fine, but just make sure you know how to check your data sheet. Go check your data sheet. What does giga stand for? You just go look at it. What does giga get replaced with? 10 to the 9. And then it's not an issue about like do I have my metric system memorized? No, it's not about that. It's just there for simplicity. Use the formula sheet. You just replace the capital G giga with 10 to the 9. That's your frequency. But we want the period. So it's just like the last question. The frequency and the period are reciprocals of each other. So we can say that it's the negative power. If you remember from Math 10, you had to take those exponent laws. And the negative power means you flip it. That's all that is. So and that's you can find that button on the calculator. Makes this really easy. This button on the calculator, x to the -1. So I just go into my calculator, I go 2 to the power 9. 2 times 10 to the power 9, so 2e9. Hit enter, you get this really very large number, 2 billion cycles every second, 2 billion hits every second, and then you just hit the -1 power, and you get 5 to the -10. So you get 5.0 times 10 to the negative 10 seconds. So remember that period is in seconds. Period is how long it takes to complete one cycle, but the frequency is the reverse of that. It's how many cycles in 1 second. So CD-ROMs were a big hit when I was a kid. Nowadays it's obviously like more digital, but like when I was a kid, burning some MP3s onto my CD and bringing it to school to listen to my Discman was a big thing. And I could get like 17 songs on a CD, and that was huge. 17 songs. Oh yeah. Nowadays you got like 5,000 songs on your hip, like no problem. So here, 25.5 hertz. That means that the CD inside the device is spinning. If you ever turn on, like, if you hit the CD button, the eject on your computer, you know, you can hear it. It's like, it's spinning in there. So it's 25.5 hertz. Remember, that's the frequency. Now, nobody likes to say the proper unit. That's why they call it hertz. The proper unit is 1/second. It's weird. Like, it's the seconds in the denominator. What is a hertz? That's exactly what we're talking about here. It's a cycle per second. So 25.5 spins in the 1 second. Okay, so then if you go with an inverse or the reciprocal here, if you do the reciprocal, so power minus 1, what happens when you go 25.5 inverse? You get about 0.0392. What would be the unit now? Seconds per cycle. And the cycle is often omitted. It's just a second. What's the period? The period is 0.03 seconds, or 0.04, whatever. Okay, so the frequency and the period are just inversely related, that power minus 1 button. They've given you the diameter of the CD, which you obviously don't need. You need the radius. So radius is 6 times 10 to the negative 2 meters. Just converting the centi. If you look on your data sheet, what is centi? Centi is 10 to the negative 2. And of course I divided it by 2 because we want the radius, not the diameter. And then determine the speed and the acceleration. So again, v is 2 pi r over t. So 2 pi 6 times 10 to the negative 2 over this 0.0392. So it's about 9.61 meters per second. And then to get the centripetal acceleration, you just take that value, square it, and divide by r, as the formula suggests. So it's 1,540 meters per second square. So just be mindful of units. The velocity and the acceleration, you guys are pretty comfortable with those units by now, meters per second and meters per second square. But make sure that you have a strong, keen understanding of the difference between frequency and period. And just a small note is this word here, like, this is the speed at the outside edge, because you're using the full radius. Like on the inner part of the disk, I'll draw it for you, the speed would be different. So we're talking about if you had a point on the outside edge of the disk, because when you're on the outside edge, you have to travel a farther distance. If you were on the inside part, it would be a different radius, and you're mapping out a different distance. Okay? So that's why they mentioned the outer edge of the CD. I think that's it, right? So there's the homework.